Hello everyone, my name is Quiroga and I would like to present our paper called A Study of Demonstration-Based Learning of Upper Body Motions in the Context of Robot-Assisted Therapy with my colleagues Alex Mitrevski and Plöger. The motivation of this study is that currently robots are being used in therapy for children with autism. It is important that these robots are adaptable easily, given that the therapist might not have programming knowledge to make the robot perform different actions. More specifically, it might be useful to include motions as part of the therapy, such as daily life activities. Namely, these activities can be brush their teeth, brush their hair, and others. We focus on learning upper body motions demonstrated by a person and reproducing them on the robot. In this case, the demonstrator is intended to be a therapist, and our main goal is to include such motions in the therapy with children with autism. The proposed solution is as follows. A demonstrator shows an action to the robot that captures this with the help of an RGBD camera. We extract the skeleton data and we send this information to the main algorithm. It will start by taking all the skeleton points for all the joints and we filter the data with a median filter. Subsequently, we calculate the position of the end effector at each step of the action. This helps us to predict if a collision is performed. If that's the case, we calculate the closest reachable point to the point that is in conflict with the robot. Then we get all the angles in the safe position. To reproduce any action, we will use a control system and the action can be reproduced at any point to show to a final user. Regarding the demonstration of the trajectory execution, the robot learns motions by observing a person's 3D skeleton, as shown in the image. Thereafter, the motions are converted to match the robot's embodiment. Every frame has the information of all the end joints at the time t, and this is mapped directly according to the relation of angles. Finally, to reproduce any action, we proposed a PID controller on the top of the built-in controller. For the self-collision avoidance model, as we can see in the image, the highest point represents the shoulder of the robot, the middle ones the elbow, and the lowest points the end effector position. To be more specific, the end effector is calculated as shown in the equation with respect of the position of the base frame, shoulder, and elbow. This point is projected outside of the robot to the nearest point reachable by the end effector. For instance, the angle of the shoulder and the elbow will be recalculated. Given the amount of solutions for the inverse kinematics problem, we chose the one that has the least accumulated error with respect to the previous positions. To evaluate our system, we perform two experiments. The first one is a quantitative evaluation where 12 pre-programmed motions were shown to 20 participants to perform a data collection, and we calculated the accuracy and error of their performance. The second experiment was a user evaluation. A demonstrator that is familiar with the system showed 5 motions to the robot, and the robot had to replicate them. This comparison was sent in a video to 76 participants for a qualitative evaluation. The survey included questions about the robot's performance and the demonstrator confidence. The calculation of the angles for the mapping is as follows. The vector formed by the wrist and the elbow and the vector formed by the elbow and the shoulder will give the angle of the elbow joint. The projection of the vector formed by the shoulder and the elbow will give the respective angles needed of the arm for the shoulder joint, pitch, and roll. And finally, the angle between the head and the neck and the collar will give the inclination of the head. The obtained results shown a clear comparison between the original capture signal, the filter data where the outliers were removed and the signal was smooth, and the compensated motions calculated in case of self-collision in the first image. In the second image, we can see that the first execution was a built-in controller onto the robot, and we improved this execution with our PID controller shown in green, where the delay is deleted and the signal has less error. The third plot shows that a significant number of predicted self-collisions were avoided by our predictive model for all demonstrated actions. It's important to clarify that those collisions were superficial and none of them interfered with the actual movement of the robot. To analyze further the system, we calculated the average reproduction error of all participants over all actions. The shaded region represent the standard deviation of the error that is clearly higher at the beginning of the executions, because the robot has started the motion in an initial random position. The deviation decreases considerably as the robot starts tracking the trajectory closely, but it's temporarily large at turning positions. The result of the survey shown that some actions were more accepted than others. It means that those can be directly used after one recording. The others have to be recorded again. For the second type of question, how easy do you think it will be to demonstrate an action to the robot? The users had confidence to perform the role of a demonstrator. And for the last question, the point of view of the camera and the speed of demonstration were the ones with most votes. As a summary, we presented a method for acquiring motions from humans and reproducing them on a robot. We collected data from human joint as a skeleton, and this data was smoothed with the help of a median filter. We use forward kinematics to predict self-collision and inverse kinematics to re-estimate the angles. Almost 98% of the predicted self-collisions were avoided. The results suggest that the method is feasible, and the accuracy is still affected by some noise. Most motions are moderately accepted by the users, and 50% of them have confidence enough to become a demonstrator. The other half might need familiarization with the system. Thank you.